This example is on polarization of an EM field. Determine the polarization of a plane wave with, and then the electric field is specified by this thing here. So let's take a look at that electric field. It has a component that points in the x direction, and it has a component that points in the y direction. And it's in a lossy dielectric because the amplitude is decreasing as e to the negative 0.25 z. So this thing is moving in the z direction. All right. So first of all, we need to consider the wave at a fixed point in space, because if it's polarized in that fixed point in space, then it's going to be polarized as it propagates through space. So we can choose any point that we like, really. And the most convenient point is, of course, z in this case equals 0, right? So we're going to consider z equals 0. That way things drop out. And why is it z? Well, this thing is propagating in the z direction. All right, so once we do that, I think things will become a little bit more clear. So I'm going to just write the mathematical expression of the wave at 0, comma t. Remember, there are two variables here, t and z. All right, so at z equals 0, the amplitude then is just of the cosine wave is just 4, and then we have cosine of omega t, and that's in the x direction. So that's the component that points in the x direction, and then we have plus 3 e to the 0, which is 1, times sine of omega t that points in the y direction, volts per meter. Okay, so right away you see the convenience of allowing z equals to 0 instead of some other choice of z. Okay, so now what we're going to do is we're going to try to relate Ex, and I'm calling this to be Ex, that's the x component of this vector, with Ey, I'm calling this to be Ey. So that we can see the trajectory, if you want to think of it as a trajectory of this thing. If we plot, Ey versus Ex for all time, does this thing stay in a circle or does it stay in an ellipse, or neither? So all of this is to say we're going to try to get rid of the variable t. Okay, so let's be concrete here. I'm letting Ex be 4 cosine omega t. That's the x component of this vector, and I'm letting Ey be 3 sine of omega t. That's the y component of this vector. So now the trick here is to, when you're dealing with circles and ellipses, is to square these things. So you'll see then that Ex squared is 16 cosine squared of omega t, and Ey squared is 9 sine squared omega t, right? Okay, so then this guy, this Ex squared guy, implies that cosine squared of omega t equals Ex squared divided by 16, and this Ey guy implies that sine squared of omega t equals Ey squared over 9. So why did I do that? Well, remember, I'm trying to get rid of t, and when you have cosine squared of an argument plus sine squared of an argument, then that's 1. So I'm going to add these two equations, so I get 1 on the left, and so hence I've gotten rid of t, and then on the right I have Ex squared over 16 plus Ey squared over 9. So again, I'm using the idea that cosine squared of x plus sine squared of x is equal to 1. I'm using that identity. That's where I get this 1 here. Okay, so now, and this is probably good enough. Hopefully you realize that this is the equation of an ellipse. If not, you could use your preferred graphing software and make a plot of this. You'll see that this is an equation of ellipse. If this 9 were equal to 16, if those were the same numbers under there, then that would be an equation of a circle. Okay, so this is ellipse, so our conclusion is that this has elliptical polarization. Okay, elliptical polarization, so we'll put a box around that. We've answered the question, and that's our final answer.